Hello and welcome back, everyone. It occurred to me that I should probably sort of add on a little addendum to the last video before we get into page 65. I need to make this a little more precise here. Technically what I have here is correct. The partial sums aren't settling down. The partial sums diverge, which means that the infinite series diverges. But if you wanted to see this in the context of alternating series, here's how you would kind of work through this. So first of all, we notice that it is alternating, right? And we identify that Bn is equal to n over n plus 1. And in fact, both 1 and 2 go wrong. First of all, the Bn's are not decreasing. They actually get bigger, right? When n is 1, you get 1/2. When n is 2, you get 2/3. When n is 3, you get 3/4, and so on and so forth. And secondly, the limit of the Bn's is not 0. In fact, the limit of these Bn's is equal to 1. Use L'Hopital's rule or whatever other method you prefer. And so, in fact, both of these break, right? And so alternating series test does not apply. And so I guess the question is, how would you show that this series diverges using what we know so far? And usually if the alternating series test does not apply for the problem that you're looking at, especially for an alternating series, try to go back to the test for divergence. The test for divergence says if the things that you're adding up, so look at this whole expression here, minus 1 to the n times n over n plus 1. If that expression does not go to 0, then there's no way for the limit or for the series to converge, okay? Well, if you think about it, what is the limit? Is there a limit of the summand? Well, you start off with minus 1/2, then the next term is, so we're just looking at the summands, not the partial sums. That's this stuff here. The next term would be positive 2/3, then minus 3/4, then positive 4/5, etc. This sequence now does not converge. So this sequence here diverges, and therefore you can't possibly add it up and expect to get something convergent. And so therefore, by test for divergence, the infinite series diverges. So just a little addendum there. And we'll see this in another example soon enough. But on to page 65. All right, so here we have an alternating series. I think we identify that pretty quickly. The Bn, what do you think? Write it down if you know it, but I think it's the non-alternating part, right? So the n squared over n cubed plus 1. So first thing you need to check, is this decreasing? Well, yes, right? As n gets bigger, you'll notice both the top and the bottom do get bigger, but the n cubed grows faster. And so Bn is decreasing. Okay, so that's good. Now, does the limit as n goes to infinity of Bn equal 0? Well, let's find out. You can use L'Hopital's rule here if you like. You can use the fact that we're going towards infinity with a rational function. So if the higher power is on the bottom, then it goes to 0. If the highest power is the same on the top and bottom, you take the limit, or excuse me, you take the ratio of the leading coefficients. And if the higher power is on top, then the limit is infinite. Well, I think we're in case 1, right, where the higher power is on the bottom. And so, yes, this does equal 0. Okay. So what you say then is by alternating series test, the sum n equals 1 to infinity, minus 1 to the n plus 1, n squared over n cubed plus 1 converges. And that's all there is to it, right? All right, so let's come here, and I drew a little circle here since you see we're going to be dealing with angles. And this will work for actually the next 2 exercises here. So it is alternating. Notice we have this minus 1 to the n factor here. And the Bn, the sort of non-alternating part, is cosine of pi over n, okay? So is are these Bn values decreasing? Well, let's look over here. When n is equal to 1, this is the angle I'm dealing with, the pi, right? And the cosine of that is -1. Okay. Now when n equals 2, the angle I'm dealing with is pi over 2. The cosine of that is 0. Then the next one, cosine pi over 3. So this is angle pi over 3 here, the green one. The cosine of that is 1/2. Then cosine pi over 4. That's what I get when I have n equals 4. The cosine of that is √2 over 2. We see that the cosine values are actually getting bigger, right? So already we see that Bn is not decreasing. So we can't apply this theorem, right? We can't apply alternating series. And so where do we go? Well, think of our discussion from just a couple minutes ago. Let's try the test for divergence. So what we're going to do is look at the sequence of just the summands. So not the partial sums, just the summands, right? And what we see is that we get, well, -1 times cosine of pi, which is +1. Then we get +1 when n equals 2 times cosine pi over 2, which is 0. Then, let's see, you get -1/2 when n is equal to 3. Then you get positive √2 over 2. Then you get, I guess technically negative cosine of pi over 5, which we don't really know. But we do know that it's slightly bigger than this value, right? And so you see these values, they're bouncing back and forth, but they're getting farther and farther away from each other, right? Because the cosine value is getting closer and closer to 1. So essentially for large n values, you're going to be bouncing back and forth between 1 and -1. And this sequence of summands diverges, therefore. So if you like, you can say the limit n goes to infinity -1 to the n cos pi over n diverges, or does not exist, excuse me. And therefore, by the test for divergence, this infinite series, because the summands do not go to 0, this infinite series must diverge. So now let's look at the next one here. So we identify first that it's alternating, no big shock there. There's the alternating part. The non-alternating part is the sine of pi over n. Okay, and now let's see, are these Bn values decreasing? Well, here is when n equals 1, this is our angle pi. The sine of that is 0. Then when n equals 2, our angle is pi over 2, the sine of which is 1. So it looks like Bn is not decreasing. And technically, you're right. But now let's watch what happens once n is at least as big as 2. So moving on to n equals 3, the sine value is now square root of 3 over 2. Then square root of 2 over 2. Then whatever sine of pi over 5 is, but we know that it's somewhere right around here. But the sine value is smaller than the previous. Then the sine of pi over 6, which we do know is 1/2. And so on and so forth, right? And so we see these sine values eventually decreasing. So we see here Bn, although it's not decreasing because it initially jumps up by 1, right? It goes from 0 to 1, and then it starts decreasing. So we say that this is eventually decreasing, which is good enough. And it's just to account for the fact that the first couple terms may kind of bounce around a little bit. But as long as it eventually starts to decrease, then that's all you need. And now the limit as n goes to infinity of sine of pi over n, the limit of these Bn values, well, we know from section 8.1 that we can move the limit inside. As n becomes large, pi over n gets very, very close to 0. So this is sine of 0, which is 0. And that's also what we need, right? So we conclude by AST, this one, the sum the sum n equals 1 to infinity minus 1 to the n sine pi over n does actually converge. All right, so that's it for this page. In the next page, on page 66, we get into the notion of absolute convergence.